Hello, everyone. Welcome to one more IBERAMIA 22 warm-up. Today, Cristina and I have the pleasure to receive our invited speaker, José Molina. Cristina, please introduce our invited speaker.
Yeah, so good afternoon, good evening, and good morning, everybody. Just one thing, this is our warm-up sessions, so we are very happy with our speakers, and today I have the pleasure to announce this invited speaker. But before, I am Cristina Garcia from Federal University of the State of Rio de Janeiro, and today we are going to present a very dear friend and also a very famous European researcher. He is very well known in his work on fusion, data fusion, and in artificial intelligence in general. And he also has experienced both academia, papers and conferences, and keynotes, but also he has a lot of experience consulting for companies. It means that he has experience on real life, solving real life examples, real life problems using artificial intelligence technique. So it's my great pleasure that he is now entering in the area that Marisa and I also work, that is explainable AI, that is a sub area of ethics and AI, and we believe that explaining what is in the black box is the first step to trust and also to verify the truth of the results of the systems that AI is being allowing people to be augmented, to have the decision making augmented. So without more ado, I want to invite Professor Molina from Universidad Carlos III de Madrid, professor catedrático, to present his speech in Explainable AI.
Okay, thank you, Cristina. Thank you, Marisa. Thank you for this invitation, and I am very happy to stay here with you and with the people that is watching these seminars, these online seminars. And okay, I think I can begin with the presentation. Okay, this is the presentation. First, I want to talk about how we work in machine learning, or when we apply machine learning to real problems. And I follow an example, a simple example in the presentation, a classical example. No, it's a law and a probable. And if you want to resolve or to apply machine learning to predict the decision about law and a problem, the sequence or the steps that you have to follow is always the same for any problem to apply machine learning in real life. No? First of all, we have to analyze the attributes, the values of the attributes, and this analysis is based on statistics analysis. You evaluate the average, the standard deviation, no? Typically. Then from this analysis, you are able to remove the outliers from the set of instance. And then you have a data set that is well formed. And from this data set, you have to select what attributes are more important or more relevant for this prediction. Then you reduce the dimension of the problem, reduce the dimension of the database. And when you have this final data set, you are able to train the machine learning technique, the classifier, typically a classifier, prediction. Okay, any techniques of machine learning. Then this is the typical way to resolve a problem. Then if we apply this typical steps to a law and probable problem, You analyze, these are the attributes, you analyze the attributes, the values, how is the histogram of each one of the attributes, and then you remove the outliers, select the attributes, and then you apply machine learning technique. In this case, I apply, for example, random forest with n equal to 20, and then you obtain a typical final solution of the machine learning technique. This is the confusion matrix. From this confusion matrix, you obtain several indicators that tell you if the machine learning technique obtain a good results or not. You can calculate the sensitivity, the specificity, precision, recall, F1, the accuracy, the random accuracy, the kappa value. Okay, you have a lot of indicators to know if the machine learning techniques is running in a good way and obtain a final good decision for your problem. But this is the end of the project. We finish the work. We can translate the model that we evaluate in the previous phase and put in the production phase. Really, we know something about how the system classifies. This is the main problem with this kind of system. When you apply machine learning to the problems, you obtain a final solution. This final solution allows you to take decision with new data, but you don't know anything about the internal process to obtain the final decision about this new data. And this is the problem when you have some data. For example, Alice, this is a data, and then the output generates the output generated by the system is no in the 80% of probability, and then you don't give the loan to Alice, and if Alice asks you why, you don't know why you don't give this loan to Alice, or how the decision is taken, or what is the meaning of this no as output of the system. And this is the problem with this kind of application. Perhaps in engineering application, when there is no people involved, many times it's not necessary to know why, how, or the meaning of the output, because in many cases in engineering problems you have to maximize the accuracy of the system, and then it's not a problem to explain how to maximize the accuracy. The problem is maximize the accuracy only. But when your data involve persons, you have the problem that persons want to know why the decision is taken. Typically, this kind of problem appears when you work with people, or we work with critical decision system, or when you work with people, you have problem with bias, and this is a big problem now in many societies, in many countries, about bias related to racial bias or gender bias or age bias. That many people think that system take decisions in a different way, considering if you have some gender or some age or some specific values in your personal data. And then it's a big problem for many of these automatic decision systems, how to show to the people that there is no bias inside these machine learning solutions. In the case of Europe, it's not only a problem of the society, it's a legal problem, because there is a regulation about artificial intelligence when they specifically express the idea that any automatic system that takes decision automatically from data should explain how the decision is taken. This is a legal point that any machine learning developer should complain to be able to insert the machine learning system in the company or in the state. And then people want that system explain the decision that is taken, but what is a system should explain decision? What is the meaning of this expression? This is the idea that explainable artificial intelligence search is how to understand the decision taken for the system. But understand the decisions has several different views. For example, we want to understand a specific decision. We want to understand why Alice, the result of the Alice analysis for the loan approval is no. And we want to know the output for this specific point, for this specific data, for this specific decision. Sometimes the view is more general, and the idea is not understand a specific decision. You want to understand the whole system, how the system is considering the different attributes and how the final decision for any point is related with the data in the input. And another view is we want to understand what the system learns from data. In this case, we want to know if the system is acquiring knowledge that is inside data that we don't see or we don't know a priori. Then we have three different levels: specific decisions, general decision of the system, or the internal decision process, and the third view is how is the information that system learn from the data. Then it's not clear, at the end it's not clear what is the meaning of understand. Understand the system, understand the decisions. And it's more clear why it's useful understanding decision, because we want to know why the system takes a decision in order to avoid bias. Okay, this is clear. And the main point of this kind of explainable artificial intelligence is, at the end, what kind of algorithms have to be used to be more unstable the decision that they taken. Okay, then when we talk about explainable, we are talking about many things, from the accuracy of the system to the understanding of one specific decision. Then there is a lot of information that we have to work with. Okay, I try to center this talk in technical aspect related with explainable or interpretable systems. Then we try to avoid human consideration, social consideration, and center in the engineering point of view of how to develop algorithms to understand the decision that they take. Why we want to develop systems that are explainable or interpretable? Okay, the first one, as I said previously, because we need to show that the system is not biased for any kind of information of the human people, the human. The second one is to show that the system does not use privacy information. Okay, if you are able to explain how the decision is taken and the people understand how the decision is taken, people see that there is no privacy information involved in this decision. Okay. The third point is if you are able to explain how the decision is taken, the system is more robust because you are able to understand that small variation in the data has a similar output or the system has a similar performance, and then the behavior of the system is consistent. Another important point is that if you are able to explain the system, you can see the causal relation between the concepts. And then you see that only causal relation are reflected in the system. There are not correlation without causal relation. And finally, if you are able to explain how the system takes decision, people trust in this kind of system, and human accepts the final decisions because they understand how this decision is taken. Okay, and this, for example, in my case, is very important because we work in engineer system where the user are able to take the final decision, and the system only support the final decision. Then for us, it's very important trust, because trust is the way in which the user take the decision that we think that is the better decision. Okay, there is some problems with these two words, no? Interpretability or explainability. When we use the word interpretability, we are trying to say that the model, the techniques, can be understood a priori. For example, if we use machine learning techniques that learn rules, the output of the system is a set of rules, and then the system is perfectly explained reading the rules. And then the system a priori is could be explainable, and this is the idea to use interpretability for this kind of system. In the other side, we have models, techniques that are not interpretable. For example, neural networks. And then the only thing that we can do is try to show how the model take decision a posteriori, with data to show how the output is taken as function of the input. And then you can show the relation between inputs and outputs and the relevance of the attributes, but you cannot translate this system in an interpretable model. Then we have two kinds of systems, no? Systems that are interpretable by design, linear system, rule system, decision trees with not many attributes. That these systems are simple, has a low complexity, has a good transparency, but they have a bad performance, as everyone knows. And for explain model, we have a set of tools that could be classified in different variables. One tools are model agnostic. They don't depend on the model. Another tools are specific for a model. One tools has a global scope. They try to explain the global system. Another tools try to explain only one decision. It's a local scope. And there is a set of tools that are in the middle, the global and local. And another variable that to classify this kind of tool is the deep. There are tools for non-deep models and tools for deep models. There is an important relation between this interpretability or explainability models with the accuracy of the model. As you see in the image, the more accuracy models, for example, deep learning models, are the less interpretable models, and only could be explainable using input and output. This is the classical graphic that relate the accuracy and the interpretability. The more simple models like logistic regression, decision trees, that are directly interpretable, has a low accuracy comparing with another models like neural networks, simple models, super vector machine. No? And then this is a big problem, because if you want a good system, you have a bad interpretable system. No? This is a trade-off between these two kind of parameters. I put here an example. Is a work that we developed in Carlos III, working with classical database about cardiovascular disease. And the idea of this work was to show that you can try to build a system that is very simple, that is very interpretable, and if the whole battery of techniques has a similar behavior, similar accuracy, you can decide to use the more simple to be more interpretable. This in this work we have the StackLog database. In feature selection, we have 3 levels: the whole attributes, 66% of the attributes, and top 33% of attributes. We use 36 classifiers to try to classify the problem with each one of these 3 feature selection methods. And we represent here, well, this is very long in the paper, but here you have a representation of the accuracy of the different classifiers with the different number of features of attributes. And then you see that more or less the system has an accuracy near of 80%. And then you can decide, instead of using a non-interpretable techniques, use a more simple techniques that obtain a similar accuracy, but is very easy to understand. This is the case in the right of the slide. You see, we compare here only the decision tree with all the features. That is more difficult to understand that the tree only with 33% of the feature. That is very simple. It's very easy. It has only 6 rules, and with 6 rules you can classify the StackLog database and obtain a 80% of accuracy. Then the first idea of this presentation is you can use a lot of different techniques, and the best option for you is use a simple technique that's easy to understand, but you have to control that the accuracy is very similar to the complex techniques. This kind of problem is known as RASHOMON effect. The idea of this RASHOMON effect is the name is from a field that is called RASHOMON effect, in which different people, several persons, see the same accident, the same situation, and each one of them explain this situation in a different way. Sometimes a very complicated way, and sometimes in a very simple, direct way. And then from this film, now there is a number of researchers that is working on this idea of Rashomon effect. The idea is that you can use many predictive models or many classifiers that have a similar accuracy. For example, you have a problem, you use linear regression, it's a very simple method, but you can select different attributes or different features to evaluate the linear regression. And then if you select randomly the attributes, you can obtain the same accuracy with any linear regression. But the problem is that if you have many linear regression models, each model implies that the attributes has a relevance. For example, when you select randomly the attributes, many attributes are out of the linear regression. Then there is no relevance. But in other linear regression, these attributes are very relevant. And in this case, you can explain, because it's linear regression, you can explain easily one linear regression. But how can you explain that different linear regression obtain the same result? And this kind of effect, the same accuracy with different models, that means, or that could be understood in a different way, is related with instability of the system. This one want to say that if you make a small change in the definition of the problem, you obtain a model that is totally different from the previous model. Then the understanding the model is not the only problem that you have, because you can obtain several models with the same accuracy, but each model understand the problem in a different way. Okay, this effect appears in linear regression, simple method, or in neural network models that are very complex. And we are talking now that this is a problem, but you can see this problem just at the contrary. No? You can use this random Rashomon effect in a positive way. If you turn the idea, if you have a problem, you can try to use or try to find the most interpretable technique when the accuracy is similar. You can use many different techniques with a similar accuracy, and you can select the system or the technique that you want. Okay, select the more interpretable technique. That is the idea of the paper that I showed you previously. Then we want to know what is the best technique that in some sense have a good accuracy and a good interpretability. No? This kind of evaluation could be done is the idea of the Rashomon curve, the Rashomon graphics. This is this kind of graphics. This kind of graphics are represent in the x-axis. You have the risk. The risk is evaluated at the inverse of the average of the accuracy. And you select machine learning techniques, for example, a decision tree, and you fix some parameters, for example, there, and you execute this technique with this parameter randomly in the selection of the other parameters any times, and you evaluate the average of the accuracy of this random execution of the technique. Then you have the average of the accuracy, and then you select the best models. You have to define the best models. For example, the 5% best models, no? Or the models that are over the 80% of accuracy. And then you have a percentage of the good of the model for this kind of problem. And then you are evaluating one of each of these points. Each point represents a specific machine learning technique with a specific parameters that is randomly executed over the problem, and you evaluate the risk and the RASHOMON index. And then you represent all these techniques, and then you have a flat part of the curve when you can obtain best results when you are using more complex techniques, and in some moment you are in the vertical part of the curve when you are using more complex techniques where they are more difficult to understand this technique, but the accuracy is very similar. Then what is the best technique? The best technique is the technique that is in the RASHOMON elbow. It is the technique that is the best, no? Is the best technique that you can understand but obtain the best accuracy for the problem. This kind of RASHOMON curve could be evaluated for real problems. This is a real problem when you can show. I try to show you this RASHOMON curve for different problems. In this case, we plot 7 points. Each point is a decision tree with a different depth, and then you can see how these curves are in the real world. No, in the real world, you see this RASHOMON curve as a real result of this kind of evaluation. Then the first idea of this talk is, first of all, you should select the most easy techniques to be interpretable if you obtain a similar accuracy or another value that you use to evaluate your system. The best the similar accuracy and the best system is the more interpretable one. This slide in this second part of the talk, this slide show you the different tools to explain artificial intelligence techniques. Here in the top you have the different taxonomy. There's local, global, or hybrid, modular, global. If there are model specific or model agnostics, and if they have sample base. And these are the different techniques that people is developing just in these 3, 4, 5 past years. We try to explain some of one of these techniques, for example, the partial dependent plots, the line, sharp, okay, some of these in detail now, and try to explain the different, because I think it's fundamental, the difference between local explanation and global explanation. Okay, when we talk about global explanation, we are talking, first, we are talking about explanation. No? Okay, they are not interpretable of the system. We are using input and output to try to explain how the system is working. Okay, when we talk about global explanation, we are talking about how to show how the model's performance changes with the attributes, or try to show if an attribute is related with the output or not, if affect to the model or not, or we want to know if how when you change the values of the data, how the output changes, okay? If you have small changes in the input and high distance in the prediction, you have problems in the model. No, this is the idea. I want to know if there is some problem in this kind of model. There is an open question: is okay, how to measure the performance of a model? How to measure the explanation? Okay, because explanation now is evaluated by the user. We show some ideas, ideas about the global explanation, but if these ideas are good or not depends on the user. There is no indicator that tells you, okay, this system is could be explainable or not. No, there is not an indicator about this. When we talk about local explanation, the idea is we want to be able to predict the results of a new data, specific data. Local explanation is based on specific data, new data, and we want to predict if the accuracy of this prediction. And then, obviously, if you have low accuracy, the explanation should be reliable. And the other thing that we want is we want to predict the behavior of the model. If you have new data, you want to know if some attributes are more important than others in the final decision, and how much this important can be measured. And the other thing that you want is try to explain for this local explanation, try to explain for a data, for a specific data, try to explain the same thing for different models. No? That you could use the same tool for different models, for random forest, or for decision trees, or for any technique. And this is the idea of consistency. Your tool is able to explain the local behavior of any model. No? It's local explanation. Okay, I try to explain now some global explanation techniques and local explanation techniques in detail. I think it's a good way to see that explanation is not interpretation or understanding of the system. It's only a way to show how the input and output are relation and how the attributes are related to obtain the output. Begin with the global explanation techniques. The first one, the first idea is a global explanation is based on language. For example, sometimes people try to explain global behavior of the system using or translated the behavior to rules. And then the idea is, okay, this tool that translates the behavior of the system to a set of rules, this language set of rules, the language of rules, is very interpretable. No? There is a way to explain globally using a language that is common for all graphs. Another important question is the transparency, because the output could be explained only as function of the input and the model. Then our explaining technique should be able to follow the decision inside the machine learning model to explain the machine learning model. Okay, there is some techniques that are able to show how the decision is taken using this input and output data. The two finally concepts about global techniques is that they should be portable. in this sense, this tool could be used with any technique. This is the idea of portability, and tools or algorithm. The complexity of the algorithm should be low, because if you try to understand a model and the complexity of the algorithm is very high, you don't understand at the end, because the algorithm does not finish. Okay, the global models are based basically based in several ideas: the relevance of the attributes, the display of the attribute features, the partial dependency plots, the transformation of the model into trees or regression or linear regression models, to fix in some point of interest the class prototypes, or using some subrogate models locally or globally to understand the model. These are the ideas behind the algorithms that try to understand the global behavior of the system. Then, for example, if we use in our example about loan approval, if we use the random forest at the beginning of the talk, we can use the result of the random forest to see the relevance of the attributes, the relevance of the future. And then, for example, you have many kinds of ways to see or to understand the system. For example, here you have for the number of trees that you use are 20. Do you remember at the beginning of the talk? No, 20, a random forest with n equal to 20. The credit history appears in all the trees, and in the first node in the red part, and in the second node in the one color, and so on. And then you have the importance of the relevance of the future as the mean. Okay, the mean of this situation in the tree. And then you have that the more important feature to take the decision is the credit history, and the second one is the co-applicant income, and the third one is the loan amount. And then you see or you understand how the system takes the decision, because it's impossible for a random forest to explain like a tree, because you have 20 trees at the same time. It's very difficult. No? And then one way to try to understand how random forest is taking the decision is looking for what is the more relevant attribute of features to take the decision. And clearly, for example, gender is not relevant attributes to take the decision. Relevant gender or education, or if you are married, is not relevant. But credit history, co-applicant income, loan amount are very important. This is a way to show this how the decision is taken inside the machine learning technique. Another way to see or to try to understand how the decision is taken is using this kind of multi-way importance plot, in which you represent the accuracy decrease and the Gini decrease when you remove a specific feature. For example, when you remove credit history, your accuracy decrease 0.12, and your Gini index decrease in more than 50. This is the more important or the more relevant attribute in this model. At the same time, you can represent the p-value, and if you see the p-value, credit history is not the more important or the more relevant attribute using the p-value related with the output. So these graphics show that your model, the random forest model in this case, your model consider credit history as the more relevant future, but statistical analysis don't consider this. Okay, you have here represent for each one of the attributes of the future that you can remove in any case and evaluate the accuracy and the Gini index, and you represent in this two-dimensional plot the position of each one of these, and it's very similar to the relevance of the future using the depth in which the concept appear in the trees. Okay, this average credit history is the more relevant in the two cases. Co-applicant income is when you see multi-way importance plot is less important than loan amount or applicant income, but okay. In any case, you are able to understand how random forest consider the different future, and this is a way to understand how random forest take the final decision, and this is a way to try to explain the decision of random forest. You can use the same graphics to try to understand how is the relations between two different futures, and you can make the same graphic but using instead of one future, two future. Okay. Another algorithm to try to understand a random forest solution is the algorithm called in trees. That is this figure is taken for the paper. When the idea of this algorithm is okay, you have a set of trees extracted from the data, and then the idea is to extract a set of rules that explain this collection of trees. Then the idea is that you are extracting rules from each of the trees, and many rules are the same rule because appear in several trees, and then you only consider the rules that are different, and then you give a value for each rule as function of the length of the rule, the specific of the rule, and then you can select the best rules to explain the system. It's not the same output. No, random forest give a different output from these rules, but the rules allows you to understand the most important decision of the random forest. For example, in our case, if you apply this algorithm in trees to our random forest algorithm, we obtain 444 rules with a length less than 6. You can prune in these rules and you obtain only 13 rules, and the 4 more important rules are shown here and are very easy to understand. This is another way to try to understand the information of how random forest is taking the decision. The another technique is the partial dependence plot, in which the idea is the following idea. We have the data set, we select one instance, select one attribute, and change the value of this attribute over the domain. And we obtain the probability of the predicted class, output class for each one of the possible values. Then we obtain a graphic like that for each one of the instances. If we represent this curve for each one of the instance, we have something like that. Okay, and these are all the partial dependence plot for the problem that we are talking at the beginning, and we obtain in one curve for each instance. And in blue, we show the average of all of this curve. This is the average. That is the average behavior for this future. One thing is that if the curve don't cross, then there are no relation with other attributes. But when the curve are crossing, they tell us that there are some relation with other attributes, and the behavior of this attribute is changing, considering the values of the other attribute. A way to see this kind of information is taking the partial dependence plot and represent the average for the value of another future. For example, this is the partial dependent plot of the applicant income, and we take each instant from the database. We take the future applicant income. If for this future we put all the values of the domain from 0 to 80,000. Okay. When we obtain all the curves, and now instead of represent the average of all this curve, we represent the average for the instance that has a credit history equal to 0, that is the blue line, and the average of all the instance that has a credit history equal to 1, that is the this is the blue, and the 0 is the red. And we show that the behavior of the output following the applicant income depends on the attribute of credit history, because the behavior is very different. This is a way to see the relation between one attribute and the other one. Another way to represent the interactions between future is make a similar algorithm, but instead of use only one dimension, using 2 dimensions. Then we select all the instance, we select 2 different futures, and put for all the instance a value for one future and for the other future. For example, here xy, and for xy we evaluate all the instance in the system and take the average of the probabilities of predicted output class and give you a color for this average probability. We have a 2-dimensional graph. This is a 3-dimensional graph because we use the color to represent the average of probabilities. Then, for example, for our problem, we have these color maps in which we are representing 2 different futures, and the color represent the probability of prediction. And then you obtain the relation between these 2 futures. Okay, this is the techniques from the global explanation techniques that use techniques to show the relevance of the futures, to show the dependence of the future of the output with the future, the dependence between two futures. And now we try to explain only one specific decision. This is the local explanation. Local explanation there are a set of algorithms to explain a specific decision. Then this approach, the local explanation, has 3 different approaches. The first one is very well known, the ceteris paribus. This technique is like the partial. Sorry, it's like one. It's one of these curve that we show here is the ceteris paribus method to show how a specific future for a specific instant is modifying the output as you are modifying this specific future. Okay, it's one of the curves that we plot in the partial dependent plots. The other 2 approaches are the breakdown plots and the line. The breakdown plots show how a prediction for a specific instant is different from the mean prediction, and how this difference is related with independent futures. And lines show how to approximate a prediction for a specific instant using a white box. A white box, in this case, a linear regression, is the first version of line. This is the breakdown plot. You have a specific point. This is appear here. Gender female, married no, dependence 0, education graduates, employment yes, applicant income 10,000, co-applicant income 0, loan amount 300, etc. The graphics show how increase or decrease the final value from the mean value depends on the attribute. Then you have the mean value is 0.698. This is the mean of all the prediction for all the data set, and the algorithm select all instance. In this case, this specific breakdown profile put 0 to all the credit history futures for all the instance, and evaluate the average probability of the output. And in this case, calculate the difference with the average probability of the original set. In this case, is minus 0.573, no, in red. After that, with this data set, with credit history equal to 0, put over all the instant, put loan amount equal to 300, and evaluate the average probability of the output. And in this case, they obtain an increase of 0.032, and is plotted in green here. And this procedure is repeated several times until the end. And at the end, you can see what future is more important in the final evaluation for this point. Okay, there is a problem with this breakdown plot, because if you take the future in change the order of the future of the attributes, then the breakdown plot is different. Okay, it's not the same value. For example, if you take this order, credit history appears at the end. In the left, you see that the credit history relevance is 0.563, and in the right is 0.214. Then there is a dependency of the values on the order that you select the attributes. There is another method to eliminate or to remove this position dependence, that is the sharp value, because it's based on the previous model, but you change all the attributes, all the order, and put any future in different position, and after that you take the average, and using a box plot, you represent the final value, the final relevance of each one of the future to take the decision over this point. Okay, it's very important that you say this is not like the relevance of the futures in the global evaluation of the system. This is the relevance of the future for this specific data, for this specific instance. Okay. Another way to analyze this how the decision is taken over one point is the line model. Okay. In this case, we have the same specific data, and then you generate a set of points in the neighborhood of this point, changes the values of the futures near of this point, and then with this set of points, you apply, in this case, a linear model. Okay, a typical linear model to predict the output. When you use a linear model, you can analyze the the relevance of the future, and then you consider only in this case only 4 attributes. You can select more attributes or less future, but with 4 attributes in this case, in this problem, you evaluate the linear model and you obtain a weight for each one of the future. And this weight of the linear model is represented in the right, like in the previous model, and gives you an explanation of what is the future that is more important in the decision for this specific point. For this specific point, the most important thing is the credit history, the loan amount, the property area, and if she is married or not. This is the 4 more relevant attributes, and the weight of each one of them represent if they are negative or positive, and the quantity. Okay. It's important that the relevance of these specific points, the relevance of the future of this specific point, is not the same that the relevance of the future of the global model, no? Because here we are working with a specific point and the neighborhood of this point, not with the global model. Okay, I try to explain you 2 things. The first one is, okay, try to select the more easy system, more interpretable system, and when you obtain the same accuracy or similar accuracy. And the second one is there is a lot of techniques to try to explain machine learning techniques, but these techniques explain the system using or showing relation between input, output, and model, and it's not an understandable explanation. Okay, what is the future? No? Because I talked to you about the present, but what is the future? Well, perhaps the future could be something like that. No, we need unified concepts, definition. We need define in the same way, for example, the relevance of the future or the color maps, or we need to fix the idea of using more complex techniques are better because the output is the accuracy of the output is better. No? It's not always true. Because in complex technique you have complex problems, and then it's possible that with simple techniques you obtain similar accuracy. Then the future of the artificial intelligence, explainable artificial intelligence, the future could be in this way, try to measure the complex and the interpretability and try to obtain values to measure what is more accuracy, what is more complex, what is more interpretable. Clearly, we need agnosis techniques to explain the models, because now many techniques are very related to the machine learning techniques. And then we need general tools able to any machine learning techniques. Another point is that clearly explanation are not easy to understand. I think that after my talk, it's clear that it's not easy to understand how the system is working. Perhaps explanation should be adapted to the knowledge of the user, and try to give an objective explanation of the system, not a representation that the user interprets as he wants. Obviously, we need to automatize explainable artificial intelligence, not make these algorithms manually, and we need a metric. We need a metric to evaluate when you apply a machine learning techniques over a data set, how the explainable is the final model, no? Because explainability does not depend directly in the techniques, in the machine learning techniques, in the model. Depends on the model and depends on the data. And then, we need an index to know how a system is interpretable. Okay, and that's all. Did you have any question?
Yes. Marisa, I am in. Are you listening to me, Molina?
Yes,
okay.
But not a lot of questions.
I have lots of questions. You are working in a very interesting, and thank you for a very interesting, thorough presentation that opened many questions. I have mine, but Marisa told me that there is a question from the audience, from YouTube. So I will let him. So can you read it? The question is from Fernando Durrier.
I think that the better way to resolve this question is to use another accuracy metric, because it's the best way to take a global decision with the curve, to obtain the points. Because if you do pairwise comparison between classes, you have several RASHOMON curves. Okay, then it's better to use another metric, for example, F1 or okay.
So I have a question related to the first part of your presentation, and you present something very interesting. So we can play between accuracy and interpretability. So it's like you can choose, a simpler model with a little bit lower accuracy, and you choose. Okay. But I was wondering if the simpler model actually is a good representation for the reality, because if we are talking about explainability, interpretability, we are talking about causality, right? So let me give you an example. Suppose I have a lot of data about how, when it's going to rain, all of the information, and also I have information about the context, and one information that I have is like the behavior of cows. Okay. And we know that before raining, for some I think that because probably they smell better than we do or whatever, they go up the hill before it rains. So if I take like a picture of that and considering the behavior of cows, I might get a simpler model that is going to tell me, okay, the cause for raining is because of cows going up hills. That makes no sense at all, but they're only highly correlated. So it's the old problem of correlation and causality, or correlation being misunderstood as causality. So have you thought about that when you are doing this trade-off between accuracy and simplicity? And also, have you thought about actually including one of the constraints, like the model needs to be at least sound or valid, or
No, but I think that the problem is at the contrary. If you have a simple model that says a simple rule, you can say, or not, this has no sense. If you have a complex model with many features and many evaluations, you don't know how the
But
decision is taken at the end.
But
Okay.
sometimes it might be like, the expression "think outside the box."
Yeah,
The example that I gave makes no sense. I'm sure that it's just like a dummy example. But sometimes, it's about creativity. It's like when you think like, wow, I haven't thought about that. But I'm just saying that I'm suggesting that part of the method would be to, okay, let's grab more information to see if this model causing this is bullshitting. So it's not that.
no,
Okay, but
but,
cows going up the hills is causing the rain, something.
but the idea to use simple model is not to simplify the information. It's that the output is very simple, and you can understand in an easy way the decision, and then you take the decision about if it has no sense or has sense, or if has bias or not. I I work with lawyers, and many times if you explain, okay, if you live in this street, you don't you probably you go to the jail. Okay, this is bias, is horrible. Okay, but I have a simple model, and I can explain you that the model says that if you live in this street, you go to the jail. If I use a very complex model, that at the end, if you live in this street, you go to the jail, you don't know that the decision is taken because you live in this street.
Okay.
That's why I say you that is the contrary. The more simple, more
better to
easy
check
understand.
about inconsistencies and prejudice and racism and things like that. Okay, I got it. Okay. Do you have any questions, Francisco? Let Francisco join us in the room. And Molina, we have just few people in the room because we are just allowed 6 people. So we have people in the backstage.
Yes. Okay, I have many questions also.
Just one, Francisco, just one.
No, just one. No, you have been talking about the need of metrics and to assess if the explainability is good or is acceptable, or but are there any benchmark to
No. There is no measure. There is no benchmark. And each tool is built by someone that thinks that is a good way to explain, but it's not really until now. There are not a standardization of explainability about the tools, about the measure, the evaluation. There is nothing related with that.
right?
And the big problem is each one interprets the output of the interpretability tool as he wants. Okay?
Yes,
use a tool, and then you say, okay, you can see here that, but it's not, perhaps not really.
Yeah, but so you base explainability in the data that the program managed by the program, but in fact in humans it doesn't work like this. I mean, explainability is if the user is the subject of the explanation. The explainability or the value of the explainability is if the user believes the explanation or not.
Okay. If you trust, no. This is the final.
Future work.
Build a system that people trust in it, and okay, it's no problem. I cannot explain anymore. It's like politics. If you vote for someone, you always trust in him.
Yeah, of like religion. I mean, why this? I mean, because I think explainability, or if a system will be able to explain, that means that it should be able to ask questions about the results. And these questions are the basic question. Who this, why do you this, for who do you this, who profit from this, how do you do this? And if the system is able to ask these questions, not just to explain the result in terms of, no, my parameter here or here, or no, then I balance this and I the formula. Well, I think this is a very big challenge for artificial intelligence.
That's in my talk. We talk about the language. If you have a tool that translates, for example, all the models into rules, and then you have a semantic representation of the decision, and then you can understand the system using rules. But clearly, when you transform the system in rules, you lose. It's not the same system. It's similar, but it's not the same. Like in the human people. Okay, you can say, okay, I do this for this reason, but tomorrow you take the different decision, but by the same reason. We are incoherent, and this is
it is an extremely interesting discussion because goes in a different area called design rationale, because it includes the rationale of the designer, of the person who adjusts the parameters of the learning technique, for the person that provide the data set. So, and also lots of politics of the goal of the company. So it's, I hope I will meet you at IBERAMIA, Molina, so we can discuss that. And let me remind everybody, is there any more questions from the audience? Marisa?
No.
Okay, so
no more questions.
Molina, I have a lot of more questions, but we went over our time.
Okay.
And I just want to remind everybody, all our audience and everybody that's going to listen to your wonderful talk, that the deadline for IBERAMIA paper submission is June 10th. Molina, I'm waiting for your paper, and and I'm waiting to talk a lot with you during the conference. And also, I want to tell you about our next invited speaker is Jean-Pierre Briot, that is going to talk about music creation with deep learning, another very interesting topic. And I hope to have you here to discuss with Jean-Pierre. So thank you very much, Molina. It was very interesting. Thank you for your time.
Thank you, Molina.
Thank
it was
you,
amazing.
everyone.
Thank you. Bye.
Atlético, Márcio Skel saying Atlético.
Atlético, ahí, Atlético.